We have three wonderful presentations for you today for our Turbo Talks in the Enterprise Intrigue track. And first up, we have Passive Bluetooth Monitoring in SCAPI with Ryan Holman. Please welcome him.
Thank you. Today I'm going to be talking about a project I've been working on for a while. And basically the aim of the project was to bring the data that we actually obtained from passive Bluetooth monitoring into a Python medium. A little bit about myself before I get started. I live in Austin, Texas. I work for an amazing company called Zifton Technologies. I'm their lead server developer. This work actually has nothing to do with my everyday hustle and bustle. It's just stuff I did in my own spare time. I have a master's degree in computer science, and this talk is going to be really fast. I have to fit it into 15 minutes, so hold on to your seats. All right, so here's what I'm going to go over. First, I'm going to hit three essential Bluetooth topics that I cherry-picked out. I think that they're really essential to understand for doing passive Bluetooth monitoring. I'm going to go over a couple projects which are basically the foundation of my project, and I wouldn't have been able to do my work without them. And then finally, I'm going to go over my work, what it is, why I did it, what I think it provides. And I have a lot of demos. I'm not going to get through all of them, but they're all included on your conference CD, so you can go through them at your own leisure. I also exported them all to PDF format, so you can read them kind of like a documentation. All right, so the first thing to understand about Bluetooth is it's built on top of a frequency hopping protocol. And basically what this means is when two devices are talking to each other, we're hopping through 79 different channels. And when we actually monitor this passively, we can only listen to one channel or a small subset of channels at a time. So this means our data that we obtain is going to be very, very sparse. Because our data is sparse, it doesn't mean that it's useless. We can actually do a lot of stuff with this data. So here, there's three things I want you to take away from this slide. The first being that BTBB stands for Bluetooth baseband. So anytime I say it or you see it, that's what I'm talking about. And basically what Bluetooth baseband is it's what we're actually passively monitoring in Bluetooth traffic. It is the lowest layer of the Bluetooth stack, and basically we need specialized hardware in order to access this layer directly. Our everyday Bluetooth devices will not be able to access this layer, and our operating system software cannot actually access this layer. The last thing I want you to take away about Bluetooth is the Bluetooth address space, basically. This is some of the more important information we can obtain from our passive Bluetooth data. And it's laid out pretty much exactly like a MAC address in our typical everyday networking protocols. The upper half being vendor specific and the lower half being device specific. And other than that, that's about all the similarity there is, because in a Bluetooth address, we actually only need the 4 lowest bytes of the address in order to make a Bluetooth connection. And so that leads me on to my next topic. We actually split these addresses out when we talk about them in Bluetooth into 3 separate sections. The illustration shows here the NAP, the UAP, and the LAP. The NAP standing for the non-significant area part. And basically what this means is we don't need it in order to make a Bluetooth connection, which is awesome because it's actually the hardest data to obtain passively from Bluetooth traffic. The UAP being the lowest part of the vendor address space, and we get this address with some Bluetooth traffic. Not with all. It actually has to have a payload within it, and we obtain this by looking at the air checking within the payload. The LAP is just given to us in all Bluetooth traffic, so we can pretty much always guarantee that it's here. And so for my project, 2 slides ago I mentioned that you need specialized hardware in order to access this layer. So I chose the Ubertooth as my medium for actually accessing this data. If you're unfamiliar with the project, it's a project created by Michael Osman, and it allows us to access the Bluetooth baseband layer. It's a small USB dongle that can send and receive data on the same frequency as Bluetooth. So some other things about it, why I chose it, right? It's small and it's cheap. My other alternatives were a USRP or USRP2, which are big and expensive. This is just something you can, stick in your pocket or have in your laptop, and no one's really going to look at you funny for using it. Something interesting about the project is Dominic Spill actually took over as the lead developer this month for the project, so there's been a lot of code movement, and this is pretty cool. And probably most importantly, the one thing to take away from the Ubertooth project is it provides a Kismet plugin. And this Kismet plugin, created by Mike Kershaw, is able to output the Bluetooth baseband data into a PCAP file. And it's this PCAP format that I actually use in my project. Super quick about this stuff. libbtb is basically a core library for the Ubertooth project. Once again, this is created by Dominic Spill and Michael Osman. And it's basically a C library which provides data structures and methods for handling and driving information from Bluetooth baseband packets, such as UAP discovery or clock discovery. And the only reason why I really mention this is it provides a Wireshark plugin. And this Wireshark plugin is probably the closest thing to my project that there is out there. It allows us to access these Bluetooth baseband PCAP files. And a lot of my architecture was derived from this Wireshark plugin as far as bit sequences and what means what within our packets. And so I wanted to incorporate this data into Python, and so I chose my medium to be Scapy. If you're unfamiliar with Scapy, Scapy is basically a Python module / framework, which is it's pretty much your go-to library for actually dealing with network traffic in Python. It provides methods for sending, creating, manipulating, altering all types of actual network data. It supports a lot of different layers, Bluetooth baseband not being one of them, so this is kind of where I came in. So in the beginning, I only had one goal for my project, and that was, let's get Bluetooth baseband traffic into Python somehow, right? And I can successfully say that I accomplished this, and I did this by creating a Bluetooth baseband layer in Scapy. And so when I first started out, I was like, okay, how am I going to get data in here? And so I took these PCAP files, and this is how I was at first able to load data into Scapy, which was really cool. But this is all post-mortem work, right? I wanted something a little more interesting. I wanted to see packets streaming down my screen as I'm analyzing them in Python. So I had two approaches here. The first being that I could have built a direct interface into the Ubertooth in order to stream the data directly into Scapy. But I chose not to do this for the first approach because it would limit people's use of my library to only using an Ubertooth, right? There's other stuff out there that can actually do this, such as the USRP, which can also output to PCAP files, right? So the route that I chose was to actually build a streamer interface for PCAP files in Scapy. And what this allows us to do is safely read from these PCAP files as other applications are writing to them. So we can read through, it's a lot like a tail-f in Linux if you're familiar. We just read through these files. When we get to the end, we stop or we sit there and we wait for more packets to come in. And so this proved to be very useful for making this cross-compatible against different hardware. And so once I was happy with this and I had all my data flowing in and I could analyze all my traffic, there's a lot of things I would do over and over and over again. So I built a lot of built-in helper methods within this library. I built methods to basically, one of the most important things is obtaining Bluetooth addresses, right? So just simple methods that would give me all unique, distinct addresses within this PCAP data. Same thing for the packet types, right? It's really useful for me if I'm looking at a PCAP file, a Bluetooth baseband PCAP file, if I know, oh, this is all poll traffic, it's pointless to me. Does this traffic have data? Does this traffic have voice? So this is a really nice function in it too, where I'm able to just get a count of what type of packet types are in here. Also, one of the more important things too, like I can only look at MAC addresses for so long before I lose my mind. So I built a couple helper methods to let us obtain other information from these. So obtain a vendor if we actually have an NAP and a UAP. We don't always have an NAP, and I've realized this. So I'm able to do a NAP reduction based on your UAP. So if you only have a UAP, I can say, okay, here's 20,000 vendors, and I can reduce this down to 30 to 60, which actually proves pretty helpful. And if you're going to try this library out, I have super verbose doc strings. So a lot of my stuff you can kind of just go through and read it like documentation. I'm very PEP 8, so my code's pretty readable. And on top of all of this too, as I was playing with a lot of this stuff, I created a lot of extensive documentation for the other projects I was using. And this is, I kind of put this stuff out there for people who might be getting into this so they don't have to spend hours and hours and hours trying to learn how to load the latest firmware onto their Ubertooth device or get all the, super hidden applications out of like a BlueZ package and stuff like that. So this stuff is linked on my website. I'll show you the link at the end. And so here's some demo code of SCAPI in progress. Does anyone here use IPython Notebook? No? It's my new favorite Python tool. So basically, IPython Notebook allows me to create this really nice documentation and execute code within a web browser for demo's sake. So first here, I'm just going to import everything from SCAPI and from my library. Now, I'm going to take a PCAP file, a Bluetooth baseband PCAP file, and create a SCAPI reader object off of it. This is stuff that is kind of given to you within SCAPI. And so let's access some data. So this isn't completely boring. So we'll look at a packet and we'll show it, right? So at first you're going to say, okay, this is Ethernet traffic. Well, my library actually is based, the very first layer of my library uses Ethernet just like the Wireshark one because they're very similar. So let's iterate through some of these packets until we find something interesting. You can see here that we actually have some Bluetooth baseband traffic. We have a UAP associated with it. This is a little bit better. SCAPI also allows us to just do summary data. And so the really nice thing about SCAPI is we can build these really short functions to just iterate through our traffic. So I'm going to say, okay, I'm going to go through all my traffic I just loaded, and I'm going to find the first packet with a payload. And everything until then, I'm just going to print out in short summary mode. We can do stuff like this. And here's our packet with the payload. Running short on time, so I'm going to skip through some of these. These are all on your conference material CDs. We can rewrite out all these packets into new PCAP files. Here's a streamer summary. So basically I said that I created a streamer for this stuff. So here, for demo's sake, I am just accessing a log that I created from Kismet. It could actually be live and being written to right now. Basically I'm able to instantiate the streamer object on it and say, okay, let's go through here. When I get to the end, stop. And basically my streamer object will remember where I am, so the next time I go to actually access this file, all these packets, I'll start from the very end. And so you can see there was nothing else being appended to it, so I'm getting nothing back. Some of the helper methods for this stuff, basically I don't have my Wireshark manufacturer file in a default location, so I'm going to tell it where it is, show you that I have some packets that I loaded. And I'm going to do a vendor lookup, right? So here I'm going to look at maybe the 6th packet here, which has this UAP. And say I do know the NAP associated to it, I can put it into this function and get back my vendor right there. But I don't, right? So let's say I'm just going to take the same function and load in my actual packet object that I was looking at, and I'm going to save it to possible vendors. You can see that I have 60 possible vendors based on this. I can pop them all open, look through this list, and for me it was really easy because I knew I was looking at an Apple device. Here's my NAP associated with it. Helper methods. This was just one of the helper methods I have built into the library in order to actually obtain all the Bluetooth addresses. Let me see real quick. I don't have enough time to go through my other demo, but I want to show you what I'm basically able to do with this data since I now have it loaded into, where's run all? So basically I'm able to go through these packets and create some really nice looking visual graphics out of them so I can see stuff, right? So I'm using a library called Python Pandas. It's kind of my data crunching library of choice. And I'm going through all of my packets within a PCAP list, taking out the important information, time, NAP, UAP, LAP, et cetera, et cetera. This is a Python Pandas table where I can actually see a lot of this data. Cool. I can see within all of my packets that this actual packet capture was only about 5 minutes long, right? I'm going to take the max date and the min date, see this stuff. I can then visualize two within these packet lists. Okay, here is all my traffic for all clients in here, who had the most traffic. I can say, okay, who had all the pertinent traffic? So I'm getting rid of information that was only ID packets or packets without data. I can then break it down by packet type. And this is all done with just like a few lines of Python code. This is just kind of stuff that, if you're familiar with pandas, it's actually just stuff you use day to day and you just kind of rip this stuff out. Break down actual LAPs by the types of traffic they sent, do time series over all this data. If you get a chance, go through. I have a pretty good write-up on all these graphs, so you can actually see what I'm doing. I don't have a lot of time, so what is the relevance of all this stuff? I supplied a way to do post-mortem and real-time analysis with these Bluetooth baseband PCAP files. And by the methods that I chose, it's compatible across different types of hardware. And these things are really easy to incorporate. All these libraries are super easy to incorporate into your other tools that you're going to be building. I rip out tools just while I'm drinking coffee in the morning with this stuff, because we're only doing this in like 1 or 2 lines of Python, which is super nice. Current and future work. Currently working on a Python library to actually interact directly with the Ubertooth in order to use all the shared library stuff that they supply. Also, I would still like to build a direct stream into the Ubertooth so I don't have to be running Kismet in the background while I'm getting a lot of these logs. The Bluetooth low energy layer, I wasn't jumping on building this layer because I didn't have any Bluetooth low energy devices at home to test with, but it's actually pretty easy for me to build. And same defaults for actually building Bluetooth baseband traffic in SCAPI. Even though we have no method of actually sending them out currently, it'd be nice to have once this functionality is built within the hardware that we use, and we'd have a medium to just directly build these packets and send them out ready to go. So here's a lot of my references. If you're looking to get into this stuff, check it out. My slides are on the conference material. And here's my contact information. If you want to learn more about this project, hacknar.com. I promise that I will update it. I'm horrible about web presence and doing things like that. But this time I'm going to try really hard. And my email, or you can follow me on Twitter. So that's it. Thank you.
All right, thank you very much, Ryan. Up next, we have Sinful Deceit with Tom Steele and Chris Patton. Please welcome to the stage.
I guess we're going to move this up here. Good afternoon. Thanks for attending our presentation. My name is Chris Patton. I'm with HackersSecurity's Security Assessment Team. Here with me is Tom Steele, also from HackersSecurity's Security Assessment Team. Our talk is specifically about bypassing SYN flow protection to actually detect valid services, similar to kind of running Nmap, that sort of thing. This talk was born from necessity through using numerous discovery engagements. More specifically, it was probably part of an overall project such as a larger penetration test. I won't bore with you all the bios and stuff like that. So. What we're trying to do is obviously discern open ports. We're trying to discern valid open ports through, as opposed to, valid open ports as opposed to. Through SYN flood. So we're not proposing a utility that is going to replace typical service detection devices, right? What we're trying to present is a utility that will kind of augment or just provide another tool as part of the tool set when you're performing service discovery. So, when do we use vulnerability scanners? We typically use vulnerability scanners during vulnerability assessments, during penetration tests, system administration, network administration, and overall troubleshooting. Numerous tools already are available. So we have Nmap, we have ScanRAN, we have Unicorn Scan. Those have been around for a while. Some of them also kind of cross over into vulnerability assessment utilities. We can automate a lot of those things through things like Nmap's Lua-based NSE scripts. In this particular instance, we're just going to show you that this is the standard router on a stick model. We have a scanner, we have the stateful firewall, and then we also have various servers in the background. The servers in the background we've actually influenced open ports on these things. We were able to, obviously we initted services, so we know that they're running in the background. We also have closed ports, et cetera. So when we go through and we perform an Nmap scan, the way this occurs is we typically pass, the SYN to the stateful firewall, and the SYN will pass, depending on if the actual policy checks are valid, it'll pass that to the back end. The back end, in turn, will, interrogate the actual service. The service will respond back to our scanner, and we'll know the state of the port, whether it's open, whether it's closed, whether it's filtered, considering, if there's actually say, for instance, a host-based firewall or something like that running on the back end. Looks something like this. Okay, we did this on SSH, HTTP, 3306 for MySQL, and then a bunch of other random ports, 100 through 200, to represent some of the SMB, traffic, that sort of thing.
Yeah, and this is just your typical SYN scan that everyone does. And
right, exactly.
This is what we're looking for: open, closed, filtered. It works. Great.
Right, exactly. All right, so when does it not work with SYN flood protection? SYN flood protection, there's a lot of open source commercial solutions, right? So we've got BST's pfSYN, we've got Juniper's SYN Protector, Cisco's TCP Intercept, those sorts of things. It becomes difficult to discern the valid ports when you're actually scanning those because we kind of have a proxied SYN connection, right? Those devices, no matter whether it's like I said, whether it's Cisco, whether it's Juniper, they're going to respond back with a proxied request. So we're going to send out a SYNAC. They're going to come back with we're going to send out a SYN. They're going to respond with a SYNAC. The Nmap scanner or whatever scanner is going to move on. We're going to run into some situations with that. It becomes much harder to discern those valid open ports from maybe other open ports that aren't necessarily valid, right? They're just proxied, and we'll more on that in a moment. Once again, we're just showing that we're not replacing any devices. We're just putting another device potentially inline that has SYN flood capability, or it could be a bolt-on. So the bolt-on might just be an update to a configuration or something like that that's going to offer SYN flood protection. Nothing groundbreaking there. Okay, so when we do perform an additional scan, so if we're performing, so for instance, an Nmap scan, we do that through an entire range. That's going to come back with open ports. We know we know that some ports are open, and then we also know that obviously some ports are closed on the back end. However, because once again we're getting a proxied request, then the ports are they're going to return as in an open state.
Yeah, I hope no one's server looks like that.
Right. So before we can actually delve in, deeper into it, we need to know what SYN flood protection is, right? SYN flood protection typically is a way to prevent SYN floods. That's pretty obvious, but it's also a way to broker a SYN request. So you might have a proxy when if someone's trying to perform a SYN flood on you. You don't necessarily want your devices in the background, right? Your target devices, the ones that they're actually wanting to flood, to be inline or actually subject to that SYN flood, right? You want some kind of device that's going to prevent that in the front end. So with that said, those SYN flood devices actually broker that request, right? You're going to send out the SYN, there's going to be a SYN ACK that creates the first session, and then there's, in the background, the interrogation's actually going on. So what happens here, actually we'll get on it in a minute. Yeah. So the other thing is you can prevent resource exhaustion, right? Resource exhaustion from adjusting queue size, et cetera, and then SYN cookies from discerning valid IPs if you've got spoofed IPs from actual valid IPs, et cetera. But we just need a legitimate response. All right. So misconceptions of the truth. This is basically some of the suggestions that we get. People have a lot of suggestions, so increase the packet delay. Okay, increasing the packet delay, whether you increase it, whether you decrease it, doesn't matter because we're sending out the SYN. We get a SYN ACK from that proxy device from SYN flood. Doesn't matter. We still got that SYN ACK. That scanner still thinks that port's open. It's gonna iterate. It's gonna increment to the next port and move on. So that's not gonna work, right? Perform a connect scan. Okay, same exact situation. However, we're sending an additional ACK. So we send the SYN ACK, and then we get the response. We think that the scanner thinks that it's open, but it still sends an additional ACK.
We all know that there's no point to running a connect scan if you have root, so
right.
Yeah, it essentially does nothing.
Okay, so use a different scan, ACK and FIN. That's not going to work. We're using a stateful firewall, so obviously the premise is that if you send that stateful firewall is going to want to know whether that session was created with a valid SYN. If it's not, then it's not going to let it pass. It's by policy, right? We all know that. Use version detection and grep results. Okay, this is the only viable solution. It's the only one that's kind of credible in a sense. And the reason for that is that obviously we're going to iterate through all the open ports, et cetera. It's going to take an extremely long amount of time to finish. So if you've got a lot of ports to go through, I mean, expect to be there for days. The other thing is you're also relying on the fact that there's version information. So for instance, we're using Nmap to do a service grind. That there's version information that's going to be returned that's going to be greppable. Like if we get those results right. Once again, it's an idea. It's not a great idea. So. At this point, we were looking for a better solution. I'm going to hand it over to Tom because he's going to actually talk about the design, the execution of kind of our research and the tool that we've developed. Thank you.
Yeah. So right now we're just looking at packet capture of an Nmap scan of 2 ports, port 80 and 4444. And on this server, I know that port 80 is open, and I've confirmed that no one shelled me and port 444 is not open. So as you can see, we send 2 SYNs at the top, and we get a SYN ACK back for port 80 because it's open, but we also get a SYN ACK back for port 4444. So SYN flood protection is enabled. Something's proxying our connections. So solution to the problem. Basically, I just dug through packet captures and started writing tools. First, I used Python and Scapy, and I created using what I call an MSS option scan. So if you guys follow my blog, I doubt it, or 6 Labs, you've seen that I created an MSS option scanner in Python, and it kind of worked. It actually worked for Juniper and IP tables, but it didn't work for Cisco, and it didn't work for F5, so I had to move on. And so I finished writing it in C and C++ using libpcap, and as you can see, we have 2 different scan types, MSS option scanning and what I'm calling connect response scanning. And it has something we call confidence scoring, which I'll get into in a minute. So MSS option scan, it's essentially a SYN scan. I'm using raw sockets to send a SYN without the max segment size set. And then in the response, I read to see if a max segment size is a size I specify. Oftentimes, it's highly dependent on firewall and firewall configuration. So basically, you want to be able to tell if the firewall is sending you a packet or the host is sending you a packet. And it's dependent on where the rule sets are. So if you have your firewall rule saying, okay, allow port 80, before your firewall rule that says, oh, SYN proxy everything, well, I'm going to get to the host before I hit the firewall. So I can kind of detect your nonsense, I guess. But yeah, it's highly dependent, and it only works some of the times. And also, I have an Nmap patch that works, so if you want to put it in Nmap, it kind of works But like I said, highly dependent on that thing. So, and the way it works is it does a SYN, and if it gets an MSS option of the size that you set, it raises the confidence score by 1 and flags that port as open. And really the main scanning type of the tool is what we call a connect and response scan. It's actually a lot like Nmap's Connect scan. It works with all implementations, and I'm not real sure it can easily be ported to Nmap. Nmap's really good for sending one packet and getting one packet back, essentially, at least in the initial discovery of open ports. It probably could be, but that was a little bit like a lot of code to write, more than I probably could tool my own. But more on that in a second. But the basic process is we call connect, and the kernel completes a 3-way handshake for us. After that's done, I immediately close the socket, which sends a FINAC to the server. The server will respond. So once we do that connect, we've moved past the 3-way handshake. So the SYN flood says, okay, you're a legit host, not SYN flooding me. Let me move you on to the, let me broker that connection with the host, the server, and move you past. And then I close the connection, and the server that I'm scanning is still going to be sending me packets. So I start listening for an ACK, a push ACK, or a FINAC. And for each response I get, I raise the confidence by 1. And so now we're going to move on to the demo. I think. Yes. Okay. So here I'm just going to show that I have a backtrack server kind of running. So you can see that the ports, I'm going to scan ports 1 through 100. So I have port 21 for FTP, SSH, and port 80 open, and you can see that. And I'm actually routing 2 VMs through a pfSense firewall with SYN proxy state. And I have basically just 2 rules, real simple. First allowing port 80 through, and then SYN proxy all other connections. Okay, so first I'm just going to Nmap. Ports 1 through 100, SYN scan. So it's pretty fast. Every port open, not working, right? So we'll just do run mook. And so I'm just going to go through the options real quick. Obviously, help interface. You have your max segment, your MSS scanning option with the size. You have a -N saying don't perform a connect scan. You have a port string standard. You have a timing. I didn't dynamically configure the timing because I didn't want to do that, so you have to use nping or another tool like that to do it yourself. And ultimately, I am hoping that Nmap just incorporates this stuff because they have all that built out, and so they can do crazy stuff and then just import my scan type. And then you have a sleep, and then you have the confidence score. Now, like I said, the confidence score gets raised by 1 each time you receive a packet that you're looking for. So what this is good for is, for instance, an F5 SYN check will actually send an ACK back from that firewall for every port. So if you have your confidence score set for 1, what does that mean? You're getting it's going to mark every port is open. So what you do is you just set the confidence score for 2, and then now you can detect legitimate ports. So it kind of as I run into new ones, I kind of have to tweak settings and do these things. And -R is really good for printing out the reason for the port is open. So I'm going to run a port scan through all 100 ports here. And pray this works. So here I'm going to do a MSS option scan, and I'm going to do a connect scan at the same time, just so I can show both. Look at it go. Cool. So as you can see, we've moved past the SYN proxy, and we've actually detected only legitimate open ports, as I showed you in the netstat output. And so you can see that port 22, once we sent that FINAC, it actually was sending an ACK. Port 21 was also doing that. And port 80, while it didn't send us any initial information, it actually responded to our FINAC and was like, okay, I'm going to close the connection with you. As well as you can see the MSS, when I did the MSS scan, that SYN scan that I did, it it actually responded with an ACK from the host, because in my firewall, you can see that I let port 80 through right here before I set up the SYN proxy rule. I lost the slide. Oh, cool. So yeah, you can download it from my website, hup234.com. There's the link. There's also a link on the main page. If you guys want to contribute to the code or tell me I did something wrong, I'm all for that. Also, if there's any people in here that are developers for Mmap or know a developer for Mmap, please let them contact me. I really want this in Mmap. And just a special thanks to Jeremy Gosney. He really helped me out with the code. Nethic runs a BSD firewall, and I was just telling him to mess with it like every other second. And Tim Elrod from my team, who was constantly breaking it, telling me my implementations didn't work until they did. So that's what we have. Thank you for coming. If there's any questions, please come talk to us. And also, Fishnet, our team, is hiring. So if you're interested in penetration testing and hacking in general, come talk to us. We want to hear from you. And there's some references in these slides are on the CD.
Thank you very much, guys. Up next, we have Ryan Reynolds and Jonathan Claudius with pretty much my favorite title of the day, Stamp Out Hash Corruption, Crack All the Things.
Okay, thanks for coming to the talk. We're going to just dive right in. This is a turbo talk, so hold on. Okay. Ooh. You got dongle?
Yeah, the dongle.
Yeah.
There you go.
Technical difficulties. All right. I'm Ryan Reynolds. I work for Crow Horwath. I pen test. I break stuff.
And my name is Jonathan Claudius. I work for Trustwave Spider Labs, and I'm a vulnerability researcher.
All right, so today we're going to talk about the different ways to extract password hashes from local Windows systems. We're not talking about DCs, we're just talking about local accounts. We're going to talk about the tools that do this password extraction from reading registry hives, and a flaw that we found in those tools that pretty much plagues a lot of the main tools that you guys probably use. A way to fix that, and we'll have a demo for you, and then we'll also release patches for several tools. All right, so just to level set here, I think a lot of people know the difference between LM and NTLM, but LM is the old Windows hashing algorithm. It pretty much has tons of security flaws. One, you can only have a password that is 14 characters or less in length. It uppercases your password and it splits it into 7-byte chunks. NTLM came around, they said, all right, we should probably stretch out that length to 128 characters, and we will care about case. The main issue here, though, with both of them is that they're not salted. So if you have the same password on System A for a user account and on System B, the hash will be the same. So we'll talk about that a little later here. But the two main ways to access hashes on Windows systems is to either inject into the LSASS process, and tools like FGDump and PWDump6 do this. They'll load a DLL right into memory. And with the debug privileges, the high level of privileges they have, they can access the hashes. The other method is registry reading. So you're literally reading the SAM Hive file, parsing through that, taking that data that you parsed out, passing it to some mathematical algorithms, which then create what we all know as LM and NTLM hashes. The nice part about the registry reading method is, one, I'm not messing around with memory. So I don't have to worry about blue boxing a system if something goes wrong, and I also don't have to fight with AV because I'm just reading a registry, and that's a normal admin thing to do. All right, story time. So how did we get here and what's going on? So was on a pen test, got onto a system with an interpreter shell, and I'm like thinking, yes, this is awesome. I'm going to dump hashes using the hash dump script, which extracts those hashes via the registry reading method. got some hashes, got an LM hash and NTLM, and I'm like, all right, awesome, LM, I'm going to throw it through rainbow tables. Didn't crack. I even had the French rainbow tables from freerainbowtables.com that's like 400 gigs. Didn't crack through that. So then I'm like, all right, I got the NTLM hash. What I'll do is I will pass it back to the system I extracted it from, because that should work. You know, that's the hash from that system. And I get a login failure. So I'm like, WTF. I'll fight the good fight with AV, I'll kill that thing, and I'll use my old standby tool, pwdump6, which injects into LSASS, and I'll get the hashes that way, just to see if, you know, maybe it's my tools or something going on, and it turns out I got completely different hashes. As you can see, via the registry method, I had an LM and NTLM hash via injection. The LM, that AAD3B4, that's not an actual hash, that's just representing blank. So there really was no LM hash stored on the system. So it's kind of like, all right, this is weird. I've seen this on multiple pen tests. I've seen this on multiple systems. What's going on? I call up some of my coworkers. I'm like, hey, have you seen this issue? They're like, yeah, I can only get those hashes via injection. I can't use the registry routing tools. I don't know what's going on. I'm like, all right, well, what did the Googles say? Whoops. The Googles say, there's a Metasploit bug report for this actually. Someone said, hey, I run into the same issue. I don't have an LM hash stored on this system, and I run the hash dump script, and I get the incorrect hashes. So this was, at this point I was like, all right, cool. I'm not insane. Other people are having this issue, but I was still frustrated. So John and I, we've known each other for several years. We occasionally meet up for beers and swap war stories about pen testing and the security scene. And I was telling him this issue. I'm like, hey, this is weird. I can't crack these hashes. And we both like to just hack up code on the weekend. So we're like, all right, we can probably get together and figure this out, reverse some code from Metasploit. He's really good with Ruby, so we figured, why not try this out? But in order to do that, we had to figure out, where do we start? And we asked ourselves, well, where do the hashes live? And it turns out they live in the SAM registry hive. And in order to, you know, obviously they're not just there in clear text, they're in this hash data binary coded in form. And in order to get to that data, we needed the sys key, which is stored in the system hive. So we need the sys key so we can read the data in the SAM hive. So, all right, sounds good. So then we're like, all right, let's open up regedit and just browse through the SAM file. And we have the, for here we have a user account, and each user account has an F key and a V key. Turns out the F key contains a lot of policy information. Information such as, you know, when does their password expire? Do they have any logon restrictions? Just policy info. The V key is where we want to play though. It has the username and it has the LM hash data and NTLM hash data. And like I said, that's not the actual hashes, it's just the data that we need to extract to pass through mathematical algorithms to get the actual LM and NTLM hashes. So all right, cool, we figured that out. So instead of like putting up tons of screenshots of hacks and binary, we figured we'd kind of do like a pseudo representation here. So that first user there has a bunch of A's and a bunch of B's. Those A's represent an LM hash and the B's represent an NTLM hash. The second user doesn't have an LM hash, they just have an NTLM hash. So this is kind of something we're going to reference throughout the presentation here. So we said, all right, cool. Now we kind of know what's going on with the structure of the Hive files here. And we said, well, what tools outside of Metasploit do this? And it turns out all those tools extract hashes or have the ability to extract hashes from just reading the registry. So we're like, wow, okay, like let's start looking to see how these tools dive into this. And so we figured out, okay, we need to play in that V key where all that good stuff is, and we need to read in to a certain offset. So we have that gray box that says, all right, this is how far we have to read into that V key before we hit the hash data. And once we have that hash data string, we need to make a couple of decisions here. We need to say, okay, does this user have an LM hash and an NTLM hash? Or just an NTLM or nothing. And so the way that these tools on this slide determine if the hashes exist or not, they say, okay, I have the string of hash data. How big is it? What's the length of it? I'm just going to measure the length. And if it's over 40 bytes, then I am going to say I have an LM and an NTLM. If it's over only 20, I'm going to do NTLM. So the main takeaway here is, hey, we have an issue because we're just saying that we're just making a guess on how to parse this based on the size of this, which leads us into the flow.
Thanks, Ryan. So what we're talking about here, the flaw, if you guys remember, Ryan was on a pen test. He extracted hashes. He gets the ones in red from Metasploit. He gets a different set from pwdump 6. This is what we're going to be talking about. So let's revisit the logic here for a second. We've got this offset that we've read into, and then what we're going to do is we're going to read to the end of the binary data structure to see what is left. And in the cases that Ryan had problems with his Metasploit stuff when he was getting the wrong hashes, he had additional data at the end of that binary stream. And we'll get to what that data is here in a second, but essentially what this does, it actually invalidates the parsing logic within these tools. So what you have here is that when we run into this additional data at the end of the binary stream for that particular user's V key, we will parse hashes always as if there's LM and NTLM hashes there, regardless of whether or not there's actually an LM hash there. So going back to the example that we talked about, if we go to make these parsing decisions, here's the first one. So the first one, like we said, we've got LM and NTLM. We're going to parse things perfectly. So we're going to grab that red data, we're going to pass it to the cryptographic algorithms, and we're going to get the right hashes. What happens here is that if we go for the second set, we're going to parse it incorrectly. So what we're going to do is we're going to be taking garbage data and stuffing it into both LM and the NTLM data that we're going to be eventually trying to abstract our actual hashes from. So this is basically what's happening in the code. So again, the data plus plus, one of the things that we wanted to figure out, well, what the heck is this data plus plus stuff? And it turns out that it's actually the password histories for that particular user. So if you enable password histories and you have no LM hashes, we'll actually run into this logic flaw. And the funny thing is this is actually a Microsoft best practice. So in enterprise, you'll see this a lot, but when the guys are creating these tools, they probably weren't testing this use case. So this is actually what the raw data looks like. We've saved you up until now. Here is actually the F key and the V key data from the registry for their particular user. You can see in the yellow boxes there, that's actually the hash data for LM and NTLM. And at the bottom here, this big, huge green blob, that's data plus plus. So when we look at our logic, we say, hey, is this bigger than 40 bytes? If data's on there, we're always going to have it greater than 40 bytes. So that's how we actually always end up in this fail case where we're going to parse the data incorrectly. But one of the things that we found was that there's actually header data earlier on in the stream. So what we can do with this is that it can help us determine whether or not there's going to be a hash there or not, so we know how to make our parsing decisions so we don't have to use size. So what we found out was that in this case is if there's a 4 in that value, it means that there's no hash present, and if there's a 14 in that value, there's always going to be a hash present. So what we can do is we don't have to guess anymore. We don't have to say, using a measuring stick approach, oh, it looks like it's this big, so it's probably this many, or it looks like this big, it's probably only one. So we can always parse the data correctly. So if we look at the bad logic example one more time, we're going to parse data like this using the current logic, and using the new logic, we're going to, one, parse the other one correctly, and parse the B data correctly. If that makes sense. So one of the things that we did, again, like Ryan said, we focused on Metasploit within our testing. That was our primary focus because that was what Ryan was having problems with. But when we started looking at the other tools, we found out that there was a lot of tools that do this incorrectly. There's a lot of tools that use this logic. So what we did is we started going through change logs and blog posts and all this like back data stuff to figure out where did all this stuff come from. And what we found out was that actually pwdump1 is one of the first tools ever to do this, implemented this logic. And as you can see, if you can see the relationships that we've drawn here, these are the influence over time. So these are how these tools influenced each other based on our research. So we thought that was kind of cool. But when you look at it from a timeline perspective, you can see that pwdump was actually created back in 97. So this is an issue that's been all the way back to 97. We've been pulling bad hashes up until now. And as you can see here, that there's samdump after that, Cain and Abel, both of those guys did it wrong. And then samdump actually figured this out. They said, oh, hey, we're getting bad hashes. Let's fix this. Let's read it a little bit different. So they actually started using the header method back in 2007. But the problem was that when creddump was created, it was created about 3 months later. And when it was created, the guy said, hey, I use samdump as my source for this. The problem is he didn't actually use the fixed source. He used the source that was broken from before. And he was one of the first guys ever to do this in a scripting language. So that scripting language being so accessible, everyone just ate it up and started using it. So you can see all these other tools pick this logic back up, this broken logic, and started using it in their tools. And there's actually current tools that are in development right now that are using this logic to perform their parsing decisions. So the big takeaways that we have are that reversing is hard. You can't always cover all the cases when you're reversing something that you don't have a blueprint for. And leveraging code is really helpful, but it can sometimes come at a cost if we expect the assumptions that were made when that code was originally written to be true up until today. And that was, a long time ago. And one of the other things that we noticed was that open source is awesome. Like Ryan and I didn't have any knowledge of the inner workings of how this process worked before, but using everyone's code, we were able to understand how it worked, how it was broken, and how we could fix it. So we do have a demonstration put together for you. And I'm going to pull it up right now. And what we've done here is we've got Windows 8 pre-release. We thought that would be a good thing because I don't think anyone's seen that, or a lot of people have seen it yet. What we're going to do here is we have a meta-interpreter shell on the system, and we're going to actually perform the hash dump, and we're going to show you how this bug manifests itself. So we're going to switch over to the desktop here, and we've got an interpreter shell, and we're going to be dumping the hashes. And within this system, we have two users. We have Frank and we have Test. Frank is using the same exact password as Test. So you can see here that the NT hash for that user, 5F1, is the exact same. So this matches up with our understanding. It's not salted. There's nothing special about this. They're using the exact same passwords and hashes. But when we go and we look at the hashes, or the history themselves, and we enable history for this particular user, and what's important here is we actually have to change the password for this user because that's what actually changes the data structure. So we're going to set it to like a temporary password like test, and then we're going to change that password right back to the original password that the Frank user is still using.
This makes the data plus plus.
Yeah, so this is actually what adds data plus plus to our data structure. So when we go back to Metasploit and we go to dump the hashes on the system using the same code, what we'll see here is that the hashes are different. And we'll highlight it here in a second. We see we have 5F1, and then for the other one, the test user, we have 072. I'm going to pause it here for a second. This is a hash that will not crack. There's nothing that you're going to be able to do with this hash. It's complete garbage. Same thing with the LM hash. So what we did is we're going to run our code now and our patch code, and we'll show you how, with no modifications to the systems, we'll pull the right hashes for this particular user. So there you have it, no more corrupted hashes. We've got the same hash for both Frank and Test. They're using the same passwords, no more hash corruption. So the last thing that we have for you is some additional stuff. Again, we focused on Metasploit as our testing tool. It was our guinea pig, but we didn't stop there. What we did do is we actually looked at other scripting language, specifically CredDump being accessible to us as a scripting language. We've developed patches for both Metasploit and CredDump. Both of those patches have been submitted to the authors. Metasploit has this code in their repository now, so if you SVN up, you'll be able to get the correct hashes when you read this method. We're also working with all these other tool developers. Not all of them are listed on this particular list, but these are the main ones that we're working with right now to get this bug out of their particular distributions. And up to this point, they've been extremely helpful. They've come back. They've been really, really helpful, trying to fix this problem in their code. And that's it. That's our talk.